Okay, so today I'm gonna introduce the all the diet tracking that I do, and basically gonna go a little overview, and then I'll talk about the first thing that I analyzed recently for other people. This is kind of just to show um, that there is some statistical significance to some of the data, and I'll get into it in a little bit. So basically, I have this Excel sheet where I keep track of pretty much anything I can think of, and I've been recording since 2019 until today. Obviously, there's times where I missed, like there's some data missing, so there's not always going to be a lot of data. So you can kind of see here, it says days of data. So that's how many data points I have for that metric. So a lot of them I have over 3 years of data, and some of the newer ones, obviously there's much less, right? So you can see here, I just started recording my grip strength in the morning, and my subjective rating of how strong I feel that day. So there's only a little bit of data there, not enough to really be useful. And it's going to show a lot stronger correlations when you have less data, because obviously there's less confounding factors when you have a smaller subset of data. So overall, when you have the larger amount of data, there's going to be a bigger spread, but if you still have a strong effect, that means it's definitely a real effect. So, or at least it's most likely a real effect, unless it's highly correlated with something else, which is actually causing the effect. So, for example, here I've got time of the last meal in the first column, and this could be, it's basically in a 24-hour clock, what time I had the meal. Negative would be the day before, so that means I fasted the whole day and the last meal was the previous day. And then I have each column has a short statistical things here. So the R squared is basically just the R squared value of that column versus the next day heart rate variability. And then the magnitude is basically, you've got the maximum spread between the maximum day and the minimum, and the same thing for the HRV, and then the slope of the linear correlation between those. So this is not really, it's basically giving you an expectation of how much of an effect on the other variable, the X variable, exerts. So in this case, having, if I had a meal at midnight versus a meal at the previous day, on average, it's giving me a lower HRV by 0.3. So it doesn't seem like very much, but I mean, it is significant. Obviously, you'll see much stronger effects for certain things, like resting heart rate and HRV are very highly correlated, and you can see that here, 0.137. It's not like a huge correlation. If you're doing a, for example, what's it called? Like a regression, and you're trying to predict exactly what it's going to be. This is not what it is. This is just showing a slight correlation. So oftentimes you'll see in large clinical studies a relative risk reduction or something like that, and these things are showing a small effect as well, right? So if we have here, this is almost 1.2 magnitude. That means that if my resting heart rate, well, this is a mistake here, the 0, but if the resting heart rate was 61 versus 85, it could be, that much different. So obviously there's going to be a few mistakes in the data because I have to enter most of these kind of manually, and I enter them usually daily or weekly, but I try most of it. The data is directly from Chronometer, where I weigh all my food and enter it. So the first one that I want to look at for now is the protein. So we look here and we can see we got the protein column and pretty much negligible effects, right? But unlike carbs and unlike calories, it's not a negative effect, right? So if there was an effect of protein, it might be positive or it might be neutral relative to everything, unlike the carbs, calories, or the time of the last meal. And the fat doesn't really have a strong effect, so we'll just ignore that one for now. So protein seems like it might be positive or neutral, or have no effect. So then I took a look and decided to see, okay, well, what about percent protein? So this is the percent of total calories that protein contributes. And we can see here, percent protein is positively correlated with a higher HRV, a lower resting heart rate, and then kind of no correlation with the other things, although it does have a positive slope. So these are all pretty much nothing. But for heart rate and HRV, it seems like it might be a positive correlation. So in order to look at that further, we've got the protein analysis. So basically, in this sheet, I took the percent protein, the HRV, and then I split it up into different groups. So here we've got the less than 10% protein group. So these are all the days that I've had less than 10% protein, which is not very many, only 8 days in the last 1,300 days total. So 1,300 days of data, and it's only been 8 days that I've had less than 10% protein. And only 5 of those 8 days have HRV data. So the data there is not very strong. Obviously, you can see on the graph here, this is not very many data points. So that negative slope here, it might not be real, right? Because if we just had a random selection of, let's say, those points, it might make it seem like it's negative there. So obviously that part is questionable, and we're going to see the statistics to see if it is actually questionable or not. Now we can see that the average HRV on less than 10% protein is lower than normal, 43.8%, but like I said, it's only 5 days. The next group is 10 to 20%, and I've got 10% increments until 40% plus protein, which is pretty rare, although I do have over 2 months of data on 40% or higher protein intake. And we can see that the HRV does increase between each of these groups. However, is it a statistically significant increase? So we can take a look at these graphs, and really I want to focus on the percent protein intake versus next day heart rate variability. And this is basically showing, now I know the trend line is not linear, and I just wanted to use the trend line to illustrate where the middle of the data is at all the points, right? So this is not saying that it's statistically accurate or significant to use that data line and say, yeah, this is exactly what I'm expecting for my heart rate variability if I eat this much protein, right? But visually, it gives an indication of, is there possibly any correlation, right? So now we do the t-test, and typically the t-test significance cutoff is 0.05, right? So that means there's a less than 5% chance of the data not being significant. And we're looking here, I've taken different groups. So we've got less than 10% protein, the heart rate variability in that group versus 10 to 20% protein. And you can see it is less than 0.05, but if we do this Bonferroni correction, which is something that a commenter suggested to me on Reddit, they said, oh, you should do a Bonferroni correction because maybe it won't be significant data. So you can see 0 to 10% versus 10 to 20%, it's not significant if you're using the Bonferroni correction. So we're using an N value of 10 because we've got 10 different comparisons here. I'm not really very familiar with the Bonferroni correction, but regardless, you could say that this might be significant and it might not be, because it is less than 0.05, but it's not less than 0.005. So, it's questionable whether or not that's a real effect on the less than 10%. So that you can imagine this column here of data points versus this one. And that's simply because there's not very many data points in the 0 to 10% range. Then we take a look at 0 to 10% versus 20 to 30%, and we've got a lot more data here, and it is more, the t-test is giving a much lower value, but it's still not as strong. So at that point, maybe there probably is an effect, but is it real? We don't really know yet, right? Okay, this one, I just wanted to make sure that's correct. HRV, HRV. HRV, HRV. Yeah. Okay, it's just double checking these to make sure I've got the right columns selected. Okay, so now we can see that pretty much comparing the 0 to 10% and 10 to 20% versus all of the other ranges do give significantly different next day heart rate variability. So if I'm eating between 10 and 20% protein and 20 and 30% protein, it is significantly different next day heart rate variability. And we can see this further. So to get a little bit of a better spread here, we've got there we go, made it linear to appease the people, because some people seem to think that you can't just put a line that's not linear if you don't want to, right? I can put a polynomial line. It's not really affecting anything, right? This is just a visual indication. Obviously, this part is not accurate at all, but in here you can see that it doesn't really matter if I'm using a linear or not, right? The correlation stays the same. So I removed the days where I'm sick and the days where I had very high intensity training. And you can see that pretty much removed just the data points that are low. So you can see here, pretty much all these data points are gone. Obviously, there's still some days where I had low heart rate variability, and that's probably because I had alcohol or something like that. And I could remove those, but I've honestly had enough of doing this protein analysis, so I'm not going to do it. I think the data is strong enough as it is without having to accommodate for alcohol or further things, right? So then I had people commenting, oh, what about your calorie intake? Because, what if your calories are confounding this, right? Because I've already adjusted for being sick or having high intensity training. So they asked, how much protein do you eat versus how many calories do you eat, right? They're like thinking, how can you have 40% protein intake and you must be on a fasting diet with like less than 1,000 calories. And you can see here, I rarely have less than 1,000 calories, and the protein is pretty much correlated with the calories strongly. 0.147, does it 152? It doesn't really matter. Okay, so 14% correlation between calories and protein, right? So on average, I do try to make sure I get a certain amount of protein, but in general, I do get more protein when I eat more calories. And that might be confounding the information, because if you remember from earlier, the calories were negatively correlated with my HRV, right? So then we're also looking, this one's just for people's information. This is not, I'm not drawing any conclusions from it, but you can see that I do in general get a higher percentage of protein when I'm around 2,000 calories than when I'm eating a larger amount of calories, right? So my amount of calories, like my percentage of protein is pretty much always over 20% on average, right? So this is an average. The average line, like the black line, is an average of the data, right? Obviously, I have days where I'm much less than 20%, but most of the time, or on average, it's 20%, right? Or more. And there is a negative correlation. So I do eat a higher percentage of protein when I'm eating less calories. Now, is it enough of an effect to ruin the t-test here? Well, we're going to see in a second. So in order to check that, we've got the calorie intake versus the next day heart rate variability. And you can see here, there is a negative correlation, and I'll make it linear for people who don't like things to be not linear. Yes, it's a negative correlation with calories and the next day heart rate variability. It's probably because of digestive effects. Like, as I eat a huge amount of calories, it's a little bit affecting the digestion. Who knows exactly, but I'm not going to speculate here about why it's happening. I just want to know what happens, right? So in order to fit the data a little bit better and adjust for the calories, I removed the sick and high intensity training days, and we get a higher R squared. It's 0.09. So, it's only explaining 9% of heart rate variability is due to the calories on a correlation basis, right? And I used this line in order to make a calorie adjusted heart rate variability, right? So the calorie adjusted heart rate variability uses that line, and it calculates what I'd expect my heart rate variability to be that day if it was adjusted for how many calories I ate. So if I ate 1,400 calories, I'm expecting my heart rate variability to be a certain number, right? So, let's see, 63. 56. Yeah. So we can see that by doing this correction, now we've pretty much entirely removed the correlation between the heart rate variability and the calories. These graphs here are just showing that the correction has normalized the data and there's no correlation anymore between the adjusted heart rate variability and the calories. These graphs aren't statistically useful. They're just a visual demonstration showing that the adjusted HRV actually adjusts for the calorie intake, right? And I put a linear one here because people hate things that aren't linear. Now, using that, I then plotted the protein and the adjusted heart rate variability. Okay, so this is the adjusted heart rate variability. It's calorie adjusted. Okay, so calorie adjusted heart rate variability versus protein, and I'll do a linear one. Okay, so it's a very slight positive correlation. It's only 2.4%. And then if I remove the sick and the high intensity training data, 3.6% correlation, okay? So I know R squared isn't necessarily a percent, but you can kind of interpret it that way to some degree. So then we do the t-tests, and at this point we've got a little bit less significance, right? The 20 to 30% versus the higher percentages is not significant, and the less than 10% to the 10 to 20% protein is also maybe not significant. And there's only a few data points, so that's obviously an issue of how much data there is. So then we still have all of these, which are highly significant, and they're less than the Bonferroni cutoff. So this is very significant data. And you could say that me eating, say, for example, 10 to 20% protein versus eating 20 to 30% protein. So the average of these data points in this between 10 and 20% versus the average of me eating between 20 and 30%, it is a statistically significant difference in my next day heart rate variability, right? So the conclusion is yes, calories and heart rate variability are correlated, right? And that is an interesting conclusion, I think, to some degree, and it's mostly due to recovery, I think, because my ability to recover is probably correlated with making sure that I get enough protein. I do have probably an above average amount of muscle mass, and I do work out, and my body needs probably more protein than the average person in order to recover, right? And you can see here, if we go and take a look at the chronometer data, that all of the amino acids have very slight positive correlations, right? With higher heart rate variability. And obviously there's certain ones which are stronger. You know, it seems like proline, tryptophan, and glutamic acid and cysteine, they don't really have very much of a positive effect, but almost none of the proteins have any negative effect on the heart rate variability. And judging by the protein analysis, there is a little bit of an effect, right? And this is the average of a very large amount of data. And obviously there's going to be spread because there's so many other factors affecting it. But there is still remaining a small positive correlation with percent protein intake and the next day heart rate variability. And that's something interesting. So I just thought I'd share this. Normally, I do not do the t-tests or any of these graphs. I just have my sheet here where I have all of these columns, right? And it kind of gives me an idea. Is there something interesting going on? Maybe, right? Or is it just due to other factors? For example, vitamin D, it shows a negative correlation. And this is probably because I supplement more vitamin D when I'm sick. But I don't supplement protein. I just eat what I'd like and sometimes have more protein when I want. So there's a lot more interesting data, but seems like most people seem to think that there's nothing to conclude from this based on the comments on Reddit. And people are saying that who knows what they're saying. Well, I mean, I did read the comments, but we'll see what people on YouTube think. So let me know what you think, and give it a like and a subscribe if you want to see more of this type of analysis. Otherwise, I'm probably not going to share this anymore, but it's something that I will do anyways. So have a good day and goodbye.